So welcome to the second to last topic for HLIB chemistry. Topic 9, redox processes. Basically there are two SL topics, oxidation and reduction, and electrochemical cells, and one HL level topic in this unit, electrochemical cells. Okay, and today we're going to focus on the first one, 9.1, oxidation and reduction. So by the end of the unit, you should know what oxidation and reduction is, so some definitions. That'll include some definitions around oxidizing reagents and reducing reagents, what variable oxidation numbers are and why they are important, and an activity series which ranks metals according to the ease in which they undergo oxidation. And for you biologists out there, the Winkler method are used to measure oxygen demand in basically water samples. Also, you should be able to deduce oxidation states, deduce the names of transition metal compounds, identify both species that have been oxidized and reduced, oxidizing and reducing agents and associated redox reactions, deduce some redox reactions, deduce if the redox reactions will actually go or not, and solve a range of redox titration problems, and finally apply the Winkler method to calculate BOD, or biological oxygen demand. So the first one is redox calculations. Okay, so from last year, you should have two definitions of oxidation. Either it's the gain of oxygen, so here we have magnesium gaining oxygen to become magnesium oxide. So you can say that magnesium has been oxidized as it has gained an oxygen, or you could say that it is the removal of hydrogen. So for example, here we have ethanol being reduced down into acetone or ethanol, and you've lost hydrogen. Okay, so the ethanol has been oxidized and it has lost hydrogen, which we looked at in the organic component of the IGCSE course last year, or 2 years ago now. Okay, and reduction therefore is either the gain of hydrogen. Okay, so here ethene has gained hydrogen to become C2H6 or ethane. So it has been reduced by the gain of this hydrogen, or it has lost oxygen. So copper oxide has been reduced by the hydrogen to form copper because oxygen has been lost. Okay, so copper oxide has been reduced as it has lost oxygen. Okay. However, as chemistry has become more sophisticated over time, it was realized a next definition was required, which is also what we looked at IGCSE. Okay, so we look at oxidation and reduction now in terms of electrons. Okay, so not only defined in changes of oxygen or hydrogen atoms, but also in terms of gain or loss of electrons. Okay, so the key matter is that oxidation is going to be the removal or loss of electrons, okay, the oil part of oil rig. Okay, so a species will become less negative or more positive if it is oxidized. And then we have reduction, which is the gain of electrons or rig. Reduction is gain, and the species will become more negative or less positive. And this combined is called redox chemistry because you have both reduction and oxidation happening simultaneously, redox. And from these definitions, we have terms like oxidizing reagent, which is a chemical substance that causes oxidation to occur. The oxidizing agent is reduced, okay, like hypochlorite, or reducing agents are a substance that causes reduction to occur. The reducing agent is said to be oxidized. Metals are good reducing agents for this. Okay, so let's see if we can work out which one of these reagents in each redox reaction is the oxidizing agent and which one is the reducing agent. Okay, so here we have 4 redox reactions. I want you to pause the video now and try and work which one is the oxidizing agent and which one is the reducing agent. Remembering the oxidizing agent is reduced and the reducing agent is oxidized. Okay, so welcome back. The first example, the magnesium is oxidized. Okay, so it must be the reducing agent. Makes sense because it's gone from 0 to +2. Okay, therefore the proton must be reduced. It's gone from +1 to 0, and it must be the oxidizing agent. And we'll learn more about oxidation numbers later in the lesson and how to determine what they are. The next redox reaction, the oxidizing agent is the thing that's reduced, so it's going to be the dichromate, okay, and the reducing agent, which is oxidized, is going to be the Fe2+. Okay, so Fe2+ goes to 3+, it's increased in terms of charge, so it must be oxidized, must be the reducing agent. Therefore, the oxidizing agent is the thing that's reduced, the dichromate. And dichromate actually is quite a famous oxidizing agent, quite commonly used. Same with the manganate. Okay, so manganate is being reduced, okay, therefore is the oxidizing agent, and manganate is a very famous oxidizing agent. And the oxalate has been oxidized, so it must be the reducing agent. And the final one is thiosulfate. Okay, it is the reducing agent. It has been oxidized, okay, and it's actually quite a famous reducing agent. And the iodine has gone from 0 elemental iodine to 1-, so it must be the oxidizing agent, for its oxidization number has been reduced. So hopefully you got 4 out of 4. Okay, so these are examples of redox agents. Okay, so oxidizing agents include oxygen, makes sense really, chlorine and other halogens. Okay, that's why they're used in bleach, for example, to oxidize your whites. Okay, iron, 3 ions, hydrogen peroxide, again quite a famous oxidizing agent, especially in biology. The manganate ion, for example, the permanganate ion, MnO4-, and dichromate, Cr2O2 2-, okay, which we looked at in the previous slide. And examples of reducing agents are hydrogen, quite a common reducing agent in organic synthesis, in organic chemistry. Carbon and carbon monoxide, again, carbon's quite a common reducing agent in organic chemistry. Metals are common reducing agents, again, in organic synthesis. Iron 2 ions, the iodide ion, and the thiosulfate ion, which we've looked at in the previous slide. So how do we work out oxidation states? Well, they're essentially used to tell us if oxidation or reduction has occurred in a redox reaction, and you can work out therefore what's oxidized and reduced, what are the reducing agents, which are the oxidizing agents, and construct therefore half equations and balance redox equations. Okay, so the number of electrons which must be added or removed to become neutral is an example of an oxidation state. Okay, so for atoms which are already 0, you don't have to take away or add electrons, so atoms have an oxidation number of 0. Cations, basically the oxidation state is going to be the charge that they have. Okay, so for sodium ion, it's going to be +1. And therefore for anions, the the oxidation state is going to be the charge again, usually -1 for the group, well, for group 7, -1, group 6, -2, group 5, -3, for example. Okay, because you have to take 1 electron to make chlorine or chloride neutral. Okay, so for cations, it's the charge. For anions, it's the charge. Simples. Okay, so let's see if we can work out the oxidation states for the following elements below. Okay, so for carbon, iron 3+, iron 2+, oxide, helium, and aluminium 3+. Okay, so what you should have got was for carbon, it's going to be 0 because it's an element. Iron 3+ is going to be 3+. That's the charge value. 2+ for iron 2+. Oxide is going to be 2- because again that's the charge on that particular species. Helium, being an atom, is going to be 0, and aluminium 3+ will be +3 as an oxidation state because that's the charge on that particular ion. Okay, so the way I break it down is using my own simple rules for determining oxidation states. Okay, so first rule, basically 8 rules. First rule is free elements are assigned an oxidation state of 0. Okay, so that's why helium has an oxidation state of 0. That's why sodium has an oxidation state of 0. The sum of the oxidation states in all atoms in a species must be equal to the net charge of the species. Okay, so that's the reason why sodium chloride would have the sum would be +1 and -1, overall 0, because chloride will be -1, and sodium ion will be +1. Overall charge is 0. Okay, so that's the sum of oxidation states is going to be 0. Okay, the alkali metals, group 1 basically, are going to be assigned an oxidation state of 1. Fluorine in a compound is always going to be assigned the oxidation state of -1. Okay, the other ones can have variable states depending on what atoms are with them in a compound. Group 2 metals and zinc and cadmium also in compounds are also assigned an oxidation state of +2. Hydrogen usually is assigned the oxidation state of +1, unless it's assigned to a metal, then it's -1. So sodium hydride, for example, the hydride would be -1. Oxygen in compounds is assigned a oxidation of -2 by and large, except when it's with hydrogen peroxide, when the oxygen becomes -1. And halogen in compounds is assigned an oxidation state of -1. So hopefully with those rules, you can work out the oxidation states of associated species within a compound. Okay, so in terms of the oxidation states of molecules, if molecules are that species, the sum of the oxidation states adds up to 0, which we saw in the last slide. Okay, so for elements, okay, basically both are the same, so they must add up to 0. So 0 plus 0 equals 0. So for hydrogen, it's going to be 0. The compounds, the carbon in CO2 will be +4. The reason why is that oxygen is going to be -2. -2 times 2 is -4. So to make that 0, okay, the sum equals 0. Carbon therefore must be +4. Okay, so it's a little diagram there about that. So it's going to be oxygen is going to be -2. -2 times 2 equals -4. So carbon must be +4. Okay, that way they get the sum of 0 for that particular compound. Okay, for CO2. And the oxygen, therefore, in CO2 must be -2. Okay, so there we go. That's kind of there illustrated in that point. Okay, this is the reason why this is because CO2 is a neutral molecule overall. Okay, the sum of the species inside it is going to be 0. For this, one element must be positive oxidation state, and the others must therefore be negative to balance the charges out. Okay, so how do you determine which one is the positive one? Basically, the more electronegative species will have the negative value. Okay, so for carbon dioxide, the electronegative species is going to be good old oxygen. Okay, and electronegativity increases across the period and decreases down the group. So in light of that, oxygen in this particular example for carbon dioxide is going to have the negative value in this species. Okay, so here are some more problems to work out. Try and work out the oxidation states of the elements other than oxygen, hydrogen, and fluorine for these particular compounds. Okay, the ones highlighted in red. So pause the video now and let's see if you can get 100%. Right, so welcome back. So these are the answers. Okay, so for the first example, sulfur is going to be +4. Okay, because oxygen in this case is -2. 2 times 2 is -4. So to balance sum of 0, it's going to be +4. Nitrogen -3. Nitrogen in this second case for NO2 is going to be +4. Okay. For ammonium, it's going to be -3. In IF7, the iodine is going to be +7 to balance out the 7 negative charges of fluorine. Okay, remembering fluorine always has to be -1, highly electronegative. Chlorine in this particular example is going to be +7. Okay, so why do I say that? Well, basically what we've got here is we've now got 2 chlorines, so you've got to be careful. Obviously, 2 times -2 is going to be 14. Okay, that's the sum of all the oxygens. So it means that you have to have +14 in order to balance that out. We have 2 chlorines. 14 divided by 2 is going to be 7. Okay, so that's how we get chlorine being +7. In nitrate, where nitrogen is +5, and nitrite, nitrogen is now +3. Okay, difference of an oxygen, which is -2. The sulfur and sulfite, is going to be +4. the sulfur in thiosulfate is going to be plus 2, okay, because again you have minus 6 for all the oxygens, so it means that, and you've got a minus 2 charge, so it means that it's going to be 4 divided by 2, which is 2 for the sulfur. And then for SO4O62 minus, it's going to be 2.5. Obviously that's a bit confusing. We'll explain why next. And for permanganate, the manganese has an oxidation state of plus 6. So for the example of a 2.5, okay, it's not a whole number. That's weird, okay, because basically you've got 4 sulfur. Where are we? So yeah, 4 sulfurs. The oxidation state must be a whole number because some are going to have an oxidation state of 3 of those 4, and others are going to have an oxidation state of 2. It's going to be an average value of those 2 oxidation states. Okay, so how do we name oxidation states? The role of oxidation states in naming species. Okay, so to avoid problems, the oxidation state is often included in the name of the species. Okay, so when we have manganese 4, okay, in Roman numerals oxide, it shows that manganese has a plus 4 oxidation state in manganese oxide. Okay, and there are other examples there. So for example, phosphorus 5 chloride and PCl5 means phosphorus has a plus 5 oxidation state. Okay, so now with that in mind with these examples, can you name the following species I've listed? So again, pausing the video now, then coming back when you think you have the answer. Okay, so the first one is lead 2 oxide. Next one is lead 2 chloride. Next one is antimony 3 chloride. Then we have titanium 4 chloride, quite a popular reagent in organic chemistry. And the last one is bromium 5 fluoride. So hopefully you got all of those correct. Okay, so then how do we determine redox with oxidation states? Oxidation and reduction in terms of electron transfer. Okay, so a lowering of the oxidation state, say from +1 to 0, the species has been reduced. An increase in oxidation state, so okay, let's write that down. So if we go from +1 to 0, that would be reduction. And it goes from 0 to +1, that would be an increase in oxidation state, and the species has been oxidized. Okay, so with those rules in mind, state if the changes involved below are oxidation or reduction, or even neither. Right, so this is what you should have got. For iron 2 plus going to iron 3 plus, there's been an oxidation. Okay, so it's gone from +2 to +3. For iodine going to iodide, we have a reduction. For fluorine going to F2O, there's been a reduction. For C2O4 2- going to carbon dioxide, there's been an oxidation. Hydrogen peroxide going to water has been a oxidation as well. Hydrogen peroxide going to oxygen has been an oxidation. Hydrogen peroxide going to water is a reduction. Okay, dichromate going to Cr3 plus, chromium 3 plus, it's a reduction. For dichromate going to CrO42 minus, it's neither, because the chromium in the species has gone from +6 to +6, nothing's changed. And the final one, sulfate to sulfur dioxide, has been a reduction in the sulfur, gone from +6 to +4. Okay, so the next step in terms of redox chemistry is to be able to balance redox half equations. So there are basically 5 steps. The first one involves the atoms, so you've got to balance the atoms of oxidation species. Okay, then the oxidation number, you have to write down the oxidation states of each. And then with the electrons, you have to balance the charge now of the both sides of the equation with electrons. Then you balance both sides of the equation with protons if there are hydrogens involved. And then finally balance the hydrogens with addition of water, and you would have balanced the half equations. Okay, so what does this actually look like in practice? Well, let's do some examples. Right, so what does it actually look like in practice? Okay, so the first problem we'll look at as an example is balancing the half reaction of iron 2 when it's being oxidized to iron 3. Okay, so the first step is working out if the number of atoms of the species that's being oxidized is going to be equal on both sides. And indeed the case for this is iron stays as iron, so it's a 1-to-1 ratio, all good. Then we have to work out the oxidation number of each of the species involved. Okay, so iron 2+, the charge is 2+, therefore the oxidation number is +2. Iron 3+ is obviously an iron number of 3+, so it's oxidation number of +3. And then we balance out the charge of both sides. This side is +2, this side is +3, so we need to have 1 electron on this side in order for it to balance out. And there we go. We've balanced both sides of the equation. That is the balanced Harvick reaction for iron 2 going to iron 3. Okay, so the next question I'll leave to you to work out through the 5 steps. Okay, this is permanganate being reduced to manganese 2+ in acidic solution. So a bit of a tip there, okay, acidic solutions. So pause the video now and see if you can get that correct. Right, so the first step is working out the species that is being reduced. Okay, so that's going to be the manganese. Okay, so number of atoms of manganese on one side has to equal the number of manganese on the other side, and that's fine. Doesn't require changing manganese to 1-to-1. Then step 2, we have to work out the formable charges or the oxidation numbers. So manganese on the left-hand side is +7, manganese 2+. So there we go. It's going to be +2 on the right-hand side. Then step 3, we add electrons to make these charges balance. So in order for +7 to become +2, you need 5 electrons. Okay, so there we go. 5 electrons on the left-hand side. Okay, so the oxidation numbers now on both sides are the same. Then we have to balance charge, okay, because we have -6 on the left-hand side and +2 on the right-hand side. So in order to do that, we have to add 8 protons into the left-hand side. Okay, that's why we say the acidic solution. Okay, so now this left-hand side is -1 plus -5 plus 8 plus 2 as a sum overall. And then the right-hand side is +2. Okay, all good. Step 4, we're all set. And then we've also got to balance out the hydrogen atoms by adding waters. Okay, so it's going to be permanganate plus 5 electrons plus 8 protons, giving manganese 2+ plus 4 H2O, because 4 times H2 is going to give your 8 protons. And there we have a balanced equation. Okay, so next question is a bit trickier. Dichromate being reduced to Cr3+. Again in a acidic solution. So again, pausing the video now and seeing if you can get the correct answer. Okay, so the first step is going to be making sure you have the same number of species undergoing oxidation or reduction on both sides. So it's going to be the chromium that's going to be reduced. Okay, so on this side, of course, due to this little subscript 2 here, on the left-hand side you have 2 chromium, therefore you've got to have 2 chromium 3+ on the right-hand side. In step 2, the 2 chromium are going to have an overall oxidation number of +6, and then the 2 chromium on the right-hand side are going to have an oxidation number of +3. Okay. So in order for that to balance out, that's going to be +12 and +6. Okay, you need 6 electrons on the left-hand side, because +12 plus -6 equals +6, to make it equal +6 on the right-hand side. Okay, then step 4, adding protons to make sure they balance out now the entire charge of the species. So on this left-hand side we have 2- plus 6- plus 14+, and that will equal a sum of +6, and that will therefore equal 2 times +3, or +6. So both charges now equal out. And then we've just got to add water to make sure the hydrogens all balance out there we go. That is the balanced equation for the reduction of dichromate into Cr3 plus in acidic solution. Okay, so now we're going to combine our two half equations. And the combination of two ionic half equations, one involving oxidation and the other involving reduction, okay, so it's a redox reaction. The equations are balanced as follows. So step one, you write out both half equations, and then we cross multiply the equations so the number of electrons in each case is the same. Then we add the sum of these two equations together to cancel out the electrons on either side. And also when we're cancelling out, it's possible that you can cancel out species that appear on both sides. Okay, so let's do an example here. The reaction between manganate 7 and iron 2+. Okay, so we've already looked at this equation. So the oxidation step is going to be iron 2 plus going to iron 3 plus an electron. And the reduction step is permanganate going to gain 5 electrons plus 8 protons to give manganese 2 plus and 4 water. Okay, so on the top we have 1 electron, on the bottom we have 5 electrons. So what we're going to do is we're going to multiply the top row by 5. Okay, that way we have 5 electrons which we can cancel out. There we go, that's what we've done now. So now the top row has become 5 iron 2 plus giving 5 iron 3 plus now and 5 electrons. And you'll notice now you have 5 electrons on the top and 5 electrons on the bottom, which can now cancel out. Okay? And that's what we've done there. Okay, so we've basically just cancelled out the 5 electrons from both sides, giving the overall reaction there. So next thing we're going to look at is titration calculations. Okay, so common titration is that of iron with manganese 7. Okay, so what happens, this is the half equation we've just looked at, or a series of half equations and overall reaction we just looked at, because permanganate has a beautiful purple color and manganese 2 plus is colorless. So if you titrate iron 2 plus against it, the purple color will eventually disappear because the manganese 7 ion is the oxidizing agent and oxidizes the ions to iron 3 plus. Okay. Another example is the titration of iodine with thiosulfate. Okay, so iodine is usually formed in the form of potassium iodide, and oxidation forms the iodide ion into forming iodine atoms or molecules by oxidizing agents such as potassium permanganate or potassium dichromate. Okay, and iodide plus an oxidizing agent like potassium permanganate or potassium dichromate leads to formation of iodine, which of course you can then test with starch plus a reduced product. Okay, there we go. So starch is then added to react with the iodine formed to make a blue-blacks complex, which some of you would have seen in biology when you're doing discussions around photosynthesis. And then this iodine is titrated against thiosulfate and removes it from the complex solution to make it clear. So it's basically this black color titrated until it is clear. And that means that you've now no longer got iodine and the starch complex. You've now got iodide ions. So basically this titration is broken down into 2 steps. You've got iodometry and iodimetry. Okay, iode. Okay, so in iodometry, the iodide is basically oxidized to iodine. Okay, it goes from -1 to 0, the iodine atom. And in iodimetry, okay, the iodine is then reduced to iodide. Okay, and an example of that would be a titration involving vitamin C. Finally, we look at the Winkler method. Okay, so it investigates biological oxygen demand, or BOD, and BOD is a measure of the dissolved oxygen needed to biologically decompose organic matter in water over 5 days at 20 degrees Celsius. So fishies, they require about 3 parts per million of dissolved oxygen to live. And the maximum oxygen solubility in water is about 0.09 grams per decimeter cubed. Okay, so if the BOD is less than 1 in terms of parts per million, you've got almost pure water. Okay, if the BOD is 5, you've got some dodgy water. If it's 10, you probably wouldn't drink it. Okay, and if it's between 100 and 400 parts per million, it's going to be waste from untreated sewage probably, and if it's massive like 10,000, it's probably wastewater from meat processing plants. Okay, because it's all being the oxygen is not being used and dissolved in the actual water. And how do you measure BOD? You use something called the Winkler method. Okay, so you've got your water sample, which is saturated in oxygen, so known concentration is reached, about 9 ppm by shaking with air. And then the sample is incubated for a fixed temperature for 5 days to allow the matter inside the sample to present to decay by microbial action. And then excess manganese 2+ is added with hydroxide to use up the remaining oxygen and convert it to manganese dioxide and water, which you see by the half equation there. Okay, so that's what's happening there. And then iodide in acidic solution. Okay, so protons are added to form iodine and water to reform the manganese 2+, and then all the solid precipitate must be dissolved in order for that to occur. Okay, so finally we use the titration we've looked at previously. The iodine is titrated with thiosulfate to release iodide ions again. This is where the starch indicator turns up, because obviously when you have iodine and starch, it'll be a blue-black complex. Then this is converted into iodide that will go to colorless. Okay, and then we use the reaction stoichiometry to determine the number of moles of oxygen left after 5 days. Okay, following the red arrows, for every mole of thiosulfate used, 1/4 mole of oxygen is used up. And then we convert to milligrams of oxygen per decimeter cubed to get the DO in PM. What is DO? That's of course the dissolved oxygen. Okay, and then convert this BOD. I'll convert this number into a BOD in parts per million, and then 9 ppm less the dissolved oxygen. Okay, so a BOD higher than 9 ppm are determined for first diluting the original sample before incubation, and then multiplying by the dilution factor. So obviously, if you've got very polluted water, there will be dilution of the original water sample. And that's pretty much all you need to know for the redox chemistry component of the subunit. And then we'll look at electrochemical cells next.